Hello, I'm Vincenzo. Topic of today is sandboxing technology on OS X. And there we go. So first off, there won't be any sandbox escape all days in this presentation. So yeah, I'm sorry if you were expecting those. I already gave away my all day of the year .1, so that's enough until next year. Second disclaimer, please, if you have questions while I speak, just ask them directly. Don't wait for me to get to the end of the presentation, because like crazy is crazy with going back and forth with slides. Just give me a headache and possibly kill people. So, what's new in Lion? Like, if you're familiar with OS X, up until like Snow Leopard, the state of security was like really, really poor. And so Apple has made some improvements on 10.7, and their claim is that now it's like fully secure because they've implemented ASLR and DEP. But we won't be talking about neither of them because, as Alex Sotirov pointed out in 2011, they don't count as innovation. What's more interesting is that like technology called sandboxing. And the reason why it's interesting, actually there are like multiple reasons why sandboxing technologies are interesting these days. First off, pretty much every browser now has a sandbox. So Safari has a sandbox, Chrome has a sandbox, Internet Explorer has a sandbox, Adobe Reader has a sandbox. And strictly speaking about OS X, the one nice thing is that I guess from the beginning of this month, every developer that wants to have an application inside the Mac App Store or wherever it's called, needs to use the sandboxing technology. So it's going to be like sandboxing on OS X is pretty widespread and kind of like dictates the state of security of the OS. So the sandbox on OS X is implemented using a framework called TrustedBSD, which was like a project based on FreeBSD by Robert Watson, who I believe is a professor at University of Waterloo. Specifically, the way the sandboxing technology is implemented is through the mandatory access control part of the FreeBSD project. So the goal of the presentation is not to explain how exactly this works, but just to make sure that you can kind of like follow what I'm saying. I have like one slide that will walk us through how the entire thing is implemented. Also, if you want more details about the actual inner working mechanism of the sandbox on OS X, you should check the Apple Sandbox white paper by Dion Blazakis. He did like a great job, and he explained the entire like sandboxing technology in great details. But just to give you an idea, so you have like your user process, and inside the user process, you have this userland library, which is like a libsystem. If you are not familiar with OS X, libsystem, basically the version of libc on OS X. Each user process can use this syscall, which is called sandbox init, and you pass the sandbox init a profile. This profile is written in a language called TinyScheme. When you have once your process has this profile sent to sandbox init will call various function inside the lib sandbox, which will basically compile the profile. And at that point, the profile will be sent to the sandbox kernel extension that will store it per process. And so the way it works is basically the TrustedBSD mandatory access control framework will ask the sandbox kernel extension whether specific actions are allowed or not. And the Sandbox kernel extension to determine whether those actions are allowed or not will walk this compiled tiny scheme profile and say, okay, yes, this process can do this action, or no, this process cannot do this action. But since like profiles could be complicated and they can contain stuff like regex for file path, there's also another kernel extension called Apple Match, which is like the only purpose of Apple Match is to match, like, for instance, a file path to a regex passed in the Sandbox profile. And so whenever the Sandbox kernel extension encounters a string in the profile that requires Sandbox regex matching, it will ask Apple Match to do the matching, and then again will either return yes, this process is allowed to perform this specific action, or no, this process is not allowed. So again, the process is pretty simple. You have like your mandatory access control framework. Each specific kernel module can register policies hook, and you have policies hook for a lot of things. Specifically on OS X, you have 3 modules that are registered to the mandatory access control framework inside the kernel. 2 of them are basically not enforcing much. But we will see in a second why they are still sort of interesting for us. And again, when a specific action is performed, all the registered hooks are queried and to see whether a process can actually perform that action. And Sandbox will, seatbelt is like the code name for the Sandbox kernel extension, and seatbelt will walk the tiny scheme profile to grant or deny action. I mentioned that there are 3 kernel extensions registered to the Mac framework inside the OS X kernel. This is interesting because inside the XNew source code, which is the name of the kernel on OS X, there are 2 macros for checking whether a specific action is allowed or not. The first macro is called macGrant, and the second macro is called macCheck. MacCheck will ask all the register modules whether a specific action is granted, and if all the modules say yes, then the action is granted. macGrant will ask all the modules, and only if all of them say no, then the action is denied. Which means that if you find somewhere in the kernel where macGrant is used instead of macCheck, then you're basically found a sandbox escape. The great thing of the Mac framework is that it allows for a great degree of granularity. You can like control file access, inter-process communication mechanisms, so like shared POSIX, shared memory, various process management stuff. So whether a process can debug another process, whether a process can fork a process. Access to the kernel interfaces. So on OS X, the kernel is like a modular kernel, and you can have your own your modules registered to it, and those modules are written in a dumbed down version of C++ that is called IOKit. And userland processes can talk to IOKit devices through what are called IOKit user classes. And so the Mac framework can also restrict access to that part, to those modules in the kernel. Also, of course, it can restrict network access. And Apple has made some changes to the original Mac framework, because a lot of things that are potentially dangerous on OS X are actually done in userland, not in kernel land. And one of them is Apple events. I'm not sure whether you are familiar with AppleScript. AppleScript is this like high-level programming language used by Apple to have applications talk to one another. So you can, with AppleScript, you can do stuff like tell iTunes to play a song or tell Finder to open a file and so forth. And the underlying mechanism that is used inside the Apple script is to actually send what are called Apple events from one application to another. So potentially, even if your application is sandboxed, but it can still send Apple events to other application, you could ask, like, I don't know, Finder to execute a file for you. And actually, I guess sort of recently, the core advisory on like Sandbox Escape was actually because of Sandbox events, because one of the older profile inside OS X didn't actually enforce the check on Apple events. So they were able from a totally like sandboxed application to get out by using Apple script. So the idea is that you can pretty much have a policy for everything. This graph is sort of all the possible actions that are that can be managed at kernel level. As I said before, Apple has made some modifications, so there are a few things that are left out. But those basically at kernel end, that's what you have. And that's a lot of stuff, like you have action on sockets, action on process, POSIX shared memory, POSIX semaphores, pipes, IOKit, and so forth. What we will see during this presentation is that even if in theory the granularity of the various of the sandbox could be pretty nice, most of the profile are really weak profiles. So yeah, potentially you can have a policy for everything, and we will see that that's not actually the case. So just to start with some like weakening of the sandbox. If you use a sandbox profile, deny everything, what you will have is not a check on all the actions. Some actions are still not hooked by the kernel module that is responsible for enforcing the sandbox. So what you see here, like the red dots, are the actions that are denied, and the other dots are the actions that are basically not checked, regardless of whatever profile you have for your application. And for instance, pipes are not checked at all. One awesome thing is that get socket option and set socket options are not checked at all. And historically, those have been a decent source of bugs at kernel land. And even nicer, if you are familiar with OS X, Mac ports are not checked at all. Mac ports are basically the mechanism used inside OS X to have processes communicate to one another through Mac, and also Mac ports are used between a process and the kernel. So they are like a pretty powerful mechanism of communication on OS X. And once, like if you have an handle to a Mac port, you can do whatever you want, because regardless of what profile you have, it's not going to do any check on it. Still, even if not the sandbox, like the Mac framework is not used at its fullest, it still looks like a pretty heavy protection to overcome. So at first, it might look like a guy trying to escape from a straitjacket. And the ideal escape is to think jailbreakme.com. So what jailbreakme.com did was to have like a remote exploit for the browser, and then to chain that remote exploit for the browser with a local exploit for the kernel. At that point, you were like out of the sandbox and done. And if you want to take this path, there are like two main things that you want to look for. First off, like the available kernel surface that is not checked at all, but there's not controlled at all by the Mac framework. And second off, to mess with IOKit interfaces. I said this already, but basically you can, like a userland process can communicate with IOKit modules inside the kernel. So you can try to find bugs in Mac traps, which are basically the same thing as syscalls in the Mac world. And you can try to find bugs in syscalls, socket options, and all the known source of bugs in kernel code. That's the first option. The second option is to look inside the profile of the application you're auditing and watch out for the string that says allow IOKit open. And this will tell you to which user client classes you can talk to. So for instance, this is taken from Safari. You can talk to IO acceleration user client, IO frame buffer shared user client, and a bunch of others. Potentially looking inside IOKit drivers or modules is a better source of bugs compared to like the bare bone kernel, but still, you never know. The other option that comes to mind is what back in the days were called shader attacks. So when I was still in high school, there were a lot. This kind of attack took place on Windows, and the idea on Windows was that you could have multiple processes on the same desktop with different privilege levels, and a process with a low privilege level could talk to a process with an high privilege level and say, hey, can you please like execute this code for me or perform this action for me? And at that point, you gained privilege escalation. On OSX, you don't have like desktops, but there are like three main sources of possible bugs related to like shader attacks. The first one is launchd. So launchd is like the most powerful userland process that you will find on OSX. It's the daemon responsible for setting up communications between processes through the Mac system. Is also the daemon responsible for spawning processes, setting environment variables, and so forth. Before the Mac Hacker Handbook came out, you could literally ask launchd, please spawn this process for me, and you were done, out of the sandbox. Unfortunately, Apple has introduced a new policy, a userland policy for the sandbox that is called job creation. And now they will actually check whether the sandbox profile allows to actually spawn processes through launchd. And I don't like to point fingers, but I'm fairly sure that that's all Dinos and Charlie's fault. The other option is to use mock RPC servers. So a lot of actions, like a lot of stuff on OSX, is not performed by the process, but is actually performed by other processes called mock servers, laying on your computer. So for instance, if you want like to copy paste something, you're actually talking to a daemon that will do the copy pasting for you. Or if you want to access the keychain, you're actually talking to a mock RPC server that will give you access to the keychain. And there are like a ton of examples of stuff that is actually performed by mock RPC servers and not by like API or the kernel. And again, the question is it possible to use any of those mock RPC servers to perform actions on your behalf? If you want to like take this path, you should watch out for the string that says allow Mac lookup. And for instance, again, this should be, I think it's from these Safari profiles, and you are allowed to access a bunch of mock RPC servers from Safari. One of them is core service D. Also, if you are interested in like mock hacking, you should read Hacking at Mac Speed by Dino Daisovi. It's one of the few sources that I was able to find that describe in details mock RPC's exploitation stuff. And the third option is AppleScript. As I mentioned before, AppleScript is used to have multiple processes communicate to each other through Apple events. We'll see a bit more about that in a bit. All right, so that's like what anybody who approaches like the sandbox on OSX for the first time would think of. But we kind of like need to do a reality check. So first question is what an app profile looks like. And to quote Justin Hsu, most app profiles are pretty fat. In the sense that they allow you to do a ton of stuff. So I wanted to actually verify this thing. And the lamest idea I had was to just count the number of lines in some relevant profiles and see which one had like more lines. So the default profile that is used by all applications coming out from the App Store is 517 lines. The profile for web process, which is basically the Safari renderer, is 215 lines, whereas the profile for the renderer process inside Chrome is 30 lines. Usually, all of those profiles start with deny everything and then allow a bunch of stuff. So this is kind of like a good indication of how permissive they are. But still, this kind of sucks. So I come up with something slightly better. This graph again, green dots are actions that are allowed by default, regardless of any like parameters or things like this. Red actions are stuff that are not allowed at all, and green dots are things that are only allowed for in some specific circumstances. For instance, you can open some files or read some files or connect to some hosts, but not to all of them. Also, while I go through these graphs, please keep in mind that not all yellow dots are created equally. This is kind of like important. So great thing about the default profile for all the application out of the App Store is that they can fork. They can fork another process. Of course, this process will inherit the same sandbox profile of the original process, but it's still like a step forward. And the other thing is that they can exec anything. So you can potentially have like a download and exec payload. So this looks kind of weak. Let's see Safari. So we have a bit more yellow here. Nice thing about the Safari profile is that you can connect and create and send and receive sockets. So you don't have the network access problem. And now let's compare this to Chrome. The renderer process sandbox for Chrome is pretty much all red. The only thing that you are allowed to do well is to use like POSIX shared memory, which is the mechanism used by Chrome to have the browser process communicate to its renderer. But a bunch of other things are just not allowed. One of them, which is, in my opinion, the most annoying one, is that you are not allowed to open any IOKit connection. So you cannot talk to any kernel module. This highly reduced like the kernel attack surface that you have at your disposal. Also, there's no network connectivity that you can get from the render process. So this kind of sucks as well. So other than like the Chrome renderer process, all the other profiles that I've seen so far look more like a chroot jail than a sandbox. The goal is not like to make sure that the attacker can't do anything on your machine. The goal is to make sure that the attacker cannot access the entire file system, which is pretty weak. And so again, if you are a penetration tester and you are trying to audit an iOS app, keep in mind those things that you can do by default with whatever profile you have. Execute files, write to a small part of the file system. You can read a larger part of the file system. You can talk to a lot of IOKit devices. And you can talk to a lot of bulk RPC servers and to LaunchD. So potentially, like, you have a pretty big attack surface. So the first thing that comes to mind is if your application has, the application you're auditing has network access, then you can straight up do download and exec payload. Of course, as I mentioned before, you're still constrained in the same sandbox profile of the original application. But it's still like it's way better to have your own process running and trying to use like another local bug versus having to chain multiple exploits in a single payload. And the other thing is that by default, if you have network access, you can grab the keychain where all the passwords are stored. Of course, the keychain is still going to be encrypted, so you would need to crack it offline, but it's a pretty, like in my opinion, it's a pretty good example of data exfiltration. So I have this super silly application that will demonstrate you that both things are possible. So this is like the Sandbox Fetch is the example application that you have on the developer portal, the Apple developer portal. And so the first thing that we're going to try is to store a file in /course/test and execute that file. And then the second thing that we want to try is to exfiltrate the keychain. So we run our Python. We run our Python server that will send a binary to our application, and here we run our application, and the binary we were sending was ls, as you can see here, /bin/ls, and this /bin/ls, if we were right, has been stored in /course/test2, which is actually the case. So you have like your download and exec. Second example is to exfiltrate the keychain. So we run our we run this simple Python server that will write the file to /temp/receivedD. So Apple server exfiltrate, and we launch our application again. So hopefully we did receive the file, and it's the correct file. So we're gonna check his MD5 hash. So that's one, and the other one is supposed to be, the other file is supposed to be this one. So they match, and potentially we have all the user passwords. We can crack them offline and get access to a bunch of interesting things. So, well, the question is, of course, at least for the applications coming out of the App Store, what happened to granularity? And as usual, is the usual like business problem. Apple is trying to force, has forced all developers to go from like no sandbox environment to a sandbox environment. And so to avoid upsetting them too much, they have created this like profile that is pretty open so that not all application will be broken because of the sandbox. Also, there are a few things that usually people, especially non-experienced developer, tend to forget. The first thing is, suppose that like your application has like a parent process, and this parent process spawn sandbox processes. The question is, does the parent process destroy all the file descriptors, or all the sockets, or the MAC ports? Because if that's not the case, then your sandbox child can still use all of them and potentially create a lot of troubles. And also, the second thing to keep in mind is that although in the InfoSec industry, apparently the end goal is to gain root on a machine, most of the time what you're actually interested in is data. So it might be like emails or pictures or SMS. So you don't actually care for root on a machine or a phone. And so even if all the Mac RPC servers were to be fully protected, and so there was no way to actually gain code execution out of them, there are still chances that you can trick some of them into giving you access to files. And so you can possibly use some of them to read like the mail spool of somebody or the SMS database or some super important PDF files. Also, there is something else that is pretty interesting as well. Again, Apple wanted to make sure that the transition from non-sandbox to sandbox was as smooth as possible. So they have introduced temporary exceptions to the sandbox profile, and those temporary exceptions allow you to do a lot of stuff. So for instance, if your App Store application needs to send Apple events, it can use this entitlement, and then out of the sudden, your application can talk to anybody on your system. So basically, the sandbox is the entire sandbox is useless. The other pretty nice thing is Mac lookup. Basically, if your application needs to talk to a specific Mac RPC server that is not enabled by default, then you can use this specific entitlement and say, okay, my application needs to talk to whatever server that does whatever weird thing that's probably not as audited as the default available ones. And finally, applications are in general restricted to this small containers where they can write files and read files from. But if for any reasons your application needs to write somewhere else or read from somewhere else, then you can use this temporary exception to read other part of the file systems. So all of these entitlements pretty much usually means that you won the game against the application, because that will terribly weaken the sandbox profile. And also the golden coins are Dave's idle suggestion. So that's the reality, is that even though the Mac framework is pretty powerful and potentially it could severely restrict the attacker's capability on a Mac system, as of today, it's more like a door with a lock instead of like escaping from a straitjacket. Also, things that usually makes me laugh when I think about sandboxing. The first one is the irony of browsers and sandboxing. Pretty much every vendor is trying to push users to move to the cloud. So mails, personal contacts, documents, wherever in the cloud. And it's super funny that the vendor that is pushing this shift the most, which is Google, is apparently the one that brags the most about their sandbox. So what this means is that basically the sandbox will prevent an attacker from going from your browser to your underlying machine. But most likely in the next few years, if this transition to the cloud actually succeed, then wherever the attacker needs is going to be inside the browser, not inside the machine. So the sandboxes will be totally worthless at that point. And about that, I have quick demo to show you. So say that you want to, say that we are in this terrible world where everything is in the cloud, and you want to steal credentials or cookies. And you are talking to, and your a victim is using Safari. I'd like you to present HTML5 application cache. The application cache was thought to make sure that mobile users could access a website as fast as possible. So basically, your browser will keep a copy of the website locally and will ask the web server whether there's an updated version of the website or not. And if there is no updated version of the website, it will just show to the user the one that it has in its database. And this also the other idea behind the application cache is that potentially user will want to use a specific web service also when they are offline, and so the application cache allows you to do so. The great thing is that on Safari there is one single application cache for the entire browser, for all the render processes. So you don't need to get out of the sandbox to actually corrupt that file and force the user to go to whatever cached website you want and steal their credentials or cookies or whatever. And so I want to show you a quick video. All right, so this is the application cache database used by Safari. It's a SQLite database. And so, we want to see what websites are inside the database, and we have this html5demos.com. Now, say that you have an exploit for the renderer process. Oh, sorry, before that. Say we are actually able to craft a SQLite database that contains a cached entry for mail.google.com. And now say that you have a memory corruption bug in one of the renderer processes of Safari. We run our exploit, we have Safari, we accidentally connect to the vulnerable page. We resume the execution and whatnot. And then we want to read the Safari database again. And now you see that in the same database, we have an entry for mail.google.com. That's awesome. So we close Safari, run Safari again. So this is persistent. Run Safari again, and then we go to mail.google.com. And we're actually going to our web page. And this could, and from this point, you have two options. The first one is you can use your web hacking foo to steal credential or cookies. Or the second option, which is the one that I like the most, is to use the same bug you used once to own the first process, to keep owning every process for every website you are interested in. So you can basically steal whatever you need from within the renderer process without escaping the sandbox. And back to the presentation. So that was the demo. The other thing that makes me laugh is the problem of data separation. So Apple is trying to push this new API to make sure that processes will use that to do IPC communication between them. And this API interface is supposed to be secure, and we trust Apple in that. The problem that I see is that most of the developers, and this is actually the case for Chrome or Safari, will actually use homemade APIs to talk to one another. So to have the sandbox children talk to the parent process. And so what this means is that we are trusting the same developers that makes mistake in parsing untrusted input, in creating a strong API for inter-process communication, where the general assumption is that the attacker won't get there. So you have complete control of whatever input, whatever data pass between the two processes. And history is full of example of things that went terribly wrong because of this sort of assumption. Think about the baseband. The assumption there was no attacker is ever gonna have a base station. And then they suddenly did, and all the GSM implementation were super buggy. and now everyone is screaming at baseband bugs. And this is exactly what's going to happen with applications, because developers think like this usually. So it was a pretty short presentation. I hope that it helped you to, especially if you are like a pen tester or wherever, to understand what's like the truth behind the app Sandbox. And I guess the takeaway is potentially it could be like a great technology, and the Chrome renderer process is one example of that. But until Apple rewrites pretty much all their core frameworks, there is no way that that this technology will actually prevent a motivated, not even that motivated attacker to gain whatever information they need. And also bragging about the new takeaway that I've just added after the recent tweets and fights over Ponium and whatnot, is that sandboxing your browser won't matter in 1.5 years or 2 years. So thanks. If you have any questions. Oh, also, shameless plug. The iOS Agar Sandbook will be out in May. If you are interested in that sort of stuff, please buy it. And thanks. That's it. Any questions? Yes.
What can you do from the Chrome Sandbox in terms of getting to the credentials and cookies? Because you did the debugging stuff.
Well, you can. Well, unfortunately, you don't have this single database for the application cache. But you most likely can talk to the browser process and ask for credentials from other websites and violate the cross-origin policy.
You can install any app you want.
Also, yeah.
That's what I covered tomorrow.
You can install every app you want. So that's pretty much a lot of stuff. Still, I mean, you don't get code execution, you don't get control over the machine, but I don't think it matters anymore. Any other questions? No, then you're free to go, and thanks for being here.